In this lesson, we're going to solve systems by elimination. The goal of elimination is the same as graphing and substitution. We're looking for the intersection point given two equations. Elimination is an algebraic method of solving systems commonly used when substitution would result in more complex algebra. And I actually found that I became really comfortable with elimination when I was in grade 10. So generally speaking, that's the method I resort to. I very rarely actually use substitution. It takes advantage of the fact that multiples of equations are equivalent equations. In other words, they're the same line. For example, let's say you have the equation x plus 2y equals 1. I can choose any number, fraction, whole number, integer, whatever I want to multiply by this equation by, and I will still have the same equation. So let's choose, let's say, -1, just for the sake of it. Actually, let's go with -2. Okay, so I'm going to multiply the whole thing by -2. So now we have -2x minus 4y equals -2. Right, I multiplied by -2. And if I were to graph both of those lines, they would be the exact same line. They would lie on top of each other. Elimination also works on the idea that you can add an equation. That is, what you add to one side, you must add to the other. That's not a new idea for you, or hopefully isn't, because we do that all the time when we rearrange equations, right? If I want to move a number that is using addition at the time, I have to subtract it from both sides, and that allows me to move that number to the other side of the equation. So we're going to use that kind of same idea here, but we're going to use it in a sense where you're thinking about the equal sign, right? So I know that 2 plus 3 is equal to 5. So I can use the 2 plus 3 and the 5 as things that I'm adding, and I'm still adding the same to both sides, right? Because they're equivalent. So ultimately, what this system is going to do is we're going to add the numbers on the left sides, and we're going to add the numbers on the right sides to create a new equation. And we'll see that we still end up with equivalent values. So I'm just going to literally add these two equations. So 2 plus 9 is 11. Positive 3 and -3 is 0. And 5 plus 6 is 11. So we got 11 equals 11. Hopefully this allows you to see that if I add the equations when we have the equal sign, then it's the same thing as adding a number, let's say. So like if I had 2 plus 3 equals 5, we can see that pretty obvious, right? 2 plus 3 does equal 5. So I could add 2 to both sides, let's say. 2 plus 2 plus 3 equals 5 plus 2, right? So it's that same idea. We're just directly adding the equations. So adding the left sides, adding the right sides, and it's still equivalent. Okay, so here's an example. Solve the system using elimination, and you've got two equations. Just like I did in substitution, I always want to number my equations, right? I'm going to be using them. It just makes it easier to refer back to them. So we'll call those equation 1 and 2. The idea behind elimination is to eliminate a variable, right? We can't solve unless we only have one variable. So the idea is to eliminate a variable. That's what elimination refers to. So I'm going to take advantage here of, this is actually already kind of set up for us. I've got a positive 3y and a negative 3y. So if I add those two things together, I have 0y, which means that the y is now irrelevant. You might also be wondering, hey Miss Lai, we have an x here that we could easily rearrange and use substitution. And that's true, and I just wanted to start off with a nice, kind of easy one for us to use. So you'll see that we could use substitution or elimination. It will get you to the same answer. I'm just choosing this example to show you for this idea. So we are going to now add the equations. So we're going to add 1 and 2 together. So we have 2 plus 1 is 3. So there's 3 x's. And we know that negative 3y and positive 3y is 0y. So there's nothing there anymore. And 6 plus 9 is 15. So now all I have to do is rearrange for x. So x times 3, the opposite of multiplication is division. So I'm going to divide both sides by 3. And that gives me 15 over 3, which is 5. So at this point we have x equals 5. And now we just have to solve for y. So we're going to have to substitute this back into one of the other equations. You can kind of see that it's not going to really matter which one. They're both going to involve a little bit of work. So you can kind of choose whichever one you like. I'm going to substitute x into equation 1. You can try the other equation if you like, just to make sure you get the same answer. So 2 times 5 minus 3y equals 6. 10 minus 3y equals 6. Negative 3y, we want to isolate y, so we're going to subtract 10 from both sides first. So 6 minus 10 is negative 4. And then we'll divide by the negative 3, so y equals negative 4 over 3. And that means that if I have two negatives, that's the same as having positive 4 over 3. So I have my two pieces of information I need. So therefore, the solution is 5 and 4/3. And you can check the work by substituting into both equations. If you substitute the x and the y into equation 1, on the left side you should get 6. And if you substitute it into equation 2, on the left side you should get 9. And that's how we would check our answers. You should do that as a habit, especially as you're getting used to the work. Now, this video is going to end up being a little bit longer than I would like, but I want you to see this other type of example. Yeah, so if I have these equations here, I'm going to number them again. So you got equation 1 and 2. And again, we want to eliminate a variable. But if you look at this quickly, you'll see that there isn't one we can do directly. There isn't one that's the same number. And actually, even using substitution here would be pretty tedious. It would result in fractions right away. As soon as we rearrange, we'd end up with fractions. So we're going to try to do this without doing that. It doesn't mean we're not going to get fractions as answers, but we're going to use whole numbers as long as we can. So if you take a look here, you can see that we're going to have to use the multiplication idea for equivalent equations. And you've got two choices. You can choose to work with the x's, so there's a 2 and a 3 there, or you can choose to work with a negative 5 and positive 4. Being opposite signs or the same signs doesn't really matter. I want to work with smaller numbers just because then I'm going to multiply by smaller numbers. So I'm going to work with the x. So we're going to use the 2 and 3. So we are going to take equation 1 and we're going to multiply it by 3. So we'll get 6x minus 15y equals 3. And then we're going to take equation 2 and multiply it by 2. Alright, so I've taken the numbers there. I've thought about a lowest common multiple, and I'm using that lowest common multiple. Alright, it's because I'm trying to get the same value here. So 3 times 2 is 6, 4 times 2 is 8, and negative 1 times 2 is negative 2. And now I need to use the idea of elimination. Here we're going to subtract. So we subtract, because then 6 minus 6 is 0. Negative 15 minus 8 is negative 23y. And 3 minus negative 2 is positive 5. So y equals negative 5 over 23. 23 is a prime number, so it's 5, so we can't reduce this anymore. And then we're going to choose an equation to solve, or to sub y into. Try to pick the one that you think looks the easiest for you. I like the idea of equation 1, because then I'm going to divide by 2 at the end instead of 3, but it will work either way. So we're going to sub into 1, which means that I have 2x minus 5 times negative 5 over 23 equals 1. 2x plus 25 over 23. And I'm going to right away get an equivalent or common denominator here. So this will make 23 over 23. And now I'm going to subtract 25 over 23 from both sides. So we get negative 2 over 23. And then x equals negative 2 over 23 times 2. The 2's cancel out nicely to make a smaller fraction of negative 1 over 23. So therefore, the solution is negative 1 over 23 and negative 5 over 23. Right, again, graphing this would be difficult. It's a fairly strange fraction. The algebraic solution gives us an exact answer. And please remember to leave them as fractions.